Good afternoon to all. On behalf of PG and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnav College, I welcome everyone to the national webinar on surprising sequences. We will start our session with Tamil Thai Valthu, followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து கெழிலொழுகும் சீராறும் வதனமென திகழ்வரத கண்டமில் எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
Once again, I welcome everyone to the national webinar on surprising sequences. Today, our resource person, Dr. R. Sivaraman, Associate Professor, PG and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnav College, Chennai. He is a member of many professional bodies. He is a founder, trustee of Pi Mathematics Association since its inception in July 2007. He is nominated as a resource person by Department of Science and Technology, Government of India in DST Inspired programs belonging to Tamil Nadu State in Mathematics. He is a life member of American Mathematical Society, Ramanujan Mathematical Society, Indian Mathematical Society, and London Mathematical Society. And he is a life member of Association of Mathematics Teachers of India, life member of Mathematics Teachers Association of India. He received many awards. National Award for Outstanding Contributions to Science and Technology Communication from Government of India, S.S. Pillai Excellence Award in Mathematics for the contributions to mathematics from Spark Matriculation School, Vellore. He won the Distinguished Teacher Award from Association of International Mathematics Education and Research. He won the Distinguished Educator Award and Best Research Scientist Award, Lifetime Achievement Award, Best Teacher Award, Distinguished Professor Award for the year 2019 from DK International Research Foundation, and Dr. APJ Abdul Kalam Global Teacher Award for the year 2019 Lifetime Achievement Award for the year 2019, Distinguished Mathematician Award given by the International Association of Research and Development Organization, Highly Regarded Educator Award for the year 2019 from American Leadership Board for Extraordinary Service, Golden Peacock Award in Best Professor category from MVLA Trust, Mumbai from the year 2019. Even International Lifetime Achievement Award from International American Council for Research and Development for the year 2019. He won the Best Researcher in Mathematics Award by ISSN Research and Scientific Organization for the year 2020. He won Research and Innovation Award from Siddhartha Education and Research Foundation, and Outstanding Scientist Award, Distinguished Researcher of the Year Award, Best Researcher Scientist in Mathematics Award, Best Researcher of the Year Award from the year 2020. He received Radhakrishna Research Fellowship Award from Global Citizens Peace Federation, Kerala in the year 2020. He won the Isaac Newton Research Scientist Award from Sarojini Research and Development Council for the year 2020. He won Best Researcher Award from EET CRS Education, New Delhi, and he won Lifetime Achievement Award for the year 2020 from Association of Scientists, Developers and Faculties. He won Albert Einstein Research Scientist Award for the year 2020 from European Institute of Applied Research, and Dr. APJ Abdul Kalam Research Fellowship Award for the year 2020 from African Moon University, Southwest Africa and USA. He received Best Researcher Award for the year 2020 from St. Martin Centre for Research and Accreditation Commission, Australia. With this brief introduction, I welcome you, sir. Now I hand over the session to you, sir.
So thanks for introducing me. I feel very happy to present this webinar, the first topic in the webinar, beginning with today. I think I shall share my screen. I will be presenting in the topic surprising sequences. Okay, I mean, there are many sequences which are very interesting and surprising also. So I will be sharing few of those with you in the coming minutes. Is my screen visible?
Yes, sir.
Hello?
Visible, sir. Yes, sir. Visible, sir.
Shall I proceed?
Yes, sir. Yes, sir.
Hello?
Yes, sir. Proceed, sir. Visible, sir. Your screen visible, sir.
So, I will begin my presentation in the topic titled Surprising Sequences. which are mainly meant to motivate young students and research scholars who are attending this webinar, not only in Dwaraka Das Govardhan Vaishnav College, but also from other colleges and various places throughout India. So I will begin with the Vaishnav sequence. Now, before I start explaining all the sequences, I will just give a brief intro of what is that I need to do here. Maybe I have taken some 7 to 8 examples of sequences which I like most and which are favorite to me. And I have avoided sequences which are very well known, which are very popularly known. Like I have not included Fibonacci sequence and other things, though I have mentioning those sequences here and there, but I'm not going to explain the whole properties of Fibonacci sequence explicitly, because those well-known sequences need not have to have any introduction or explanation with the students community, because there are many interesting and very easy sequences which everyone knew. So I am introducing or discussing sequences which are not quite well known, but they are very interesting and surprising also. That is the motivation behind this lecture. So I will start introducing what is called Wythoff sequence, named after mathematician Wythoff. And this sequence was introduced only some 3 or 4 decades before, not a very ancient sequence. So the Wythoff sequence goes like this way. In the first row, you take Fibonacci sequence 0. You start with 0, 1. You know Fibonacci sequence works with the fashion that you assume 2 numbers, initial numbers, then the rest of the numbers is sum of the 2 previous numbers, as you all know. So I start with 0 and 1 here. So the third term is 0 plus 1, 1. Then the fourth term is 1 plus second term plus third term, which is 1 plus 1, that is 2. The fifth term, the sum of these 2 terms, third term and fourth term, which is 1 plus 2, that is 3. And 2 plus 3 is 5, 3 plus 5 is 8, and so on and so forth. So the first row actually that we have written here is precisely the Fibonacci sequence. The second row starts with 1 and then with 3. Then, as we did in Fibonacci sequence, we are adding the 2 terms to get the next term. Okay. So 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, 7 plus 11 is 18, 11 plus 18 is 29, and so on and so forth. So the first rows are numbers corresponding to Fibonacci sequence. Second row are numbers corresponding to Lucas sequence, named after French mathematician Edward Lucas. Okay. Now the rest of the rows that I need to construct here, I'm choosing some numbers here. The rule is same. Like I start with the 2 initial terms, 2 and 4, then add them to get 6. Then 4 plus 6 is 10, 6 plus 10 is 16. 10 plus 16 is 26, 16 plus 26 is 42, 26 plus 42 is 68, and so on. Similarly, I leave this as exercise for students. In fact, I have given the next row terms here. So the fourth row goes like this, and fifth row goes like this, and so on. So you see the interesting aspect of constructing this kind of terms in each row, beginning with this here. 1, 2, 3, 5, 8, 13. That is here the terms of Fibonacci sequence, the terms of Lucas sequence, and all those things. The rule of construction for each row is same. Okay. Now, how do you choose the first 2 columns? The first column here is quite simple. You see, it starts with 0, then 1, 2, 3, 4. So the whole numbers written here consecutively in the first column, beginning with 0, then 1, 2, 3. So that's easy to guess the first column. The second column needs little explanation. What you do is, this number 1 is corresponding to the construction of Fibonacci sequence. So what you do is, for the next case, beginning with 1, you take the element after 1 here. After 1 in the first row is 2, you add 1 to it, that is 3. Suppose if I start with 2 here, you take the element after 2 here. So the element after 2 here in the first row is 3, add 1 to it, that is 4. So if I start with 3, you take the element after 3 here in the first row, which is 5, add 1 to it, you get 6. If you take element 4 here, you take an element which is just greater than 4, which is 5, and then go to this column here. For 4, of course, you take element greater than 4, then add 1 to it, you get 8. And similarly, you for 5 you get 9, and so on and so forth. So this is how you have to construct the numbers in the second column. And then the rows can be constructed by adding subsequent two numbers in each row. That is quite simple. And so you get this kind of set of numbers in the grid form, you see. And what speciality that we have, so this set of numbers written here in each row is actually constitute what is called Wythoff sequence, which is constructed from very simple rule. Okay, now you see all the natural numbers are represented here. All the numbers are represented exactly once in different places. So supposing if I want to find 10 here, 10 is located only at this place in the third row, second column. Supposing if you want to locate number 15, 15 is here below 10 here in the fourth row, second column. So in other words, in mathematical terms, this terms of Wythoff sequence arranged in each row has a 1-1 correspondence with set of all natural numbers. So there is the construction of Wythoff sequence is very simple, beginning with first two rows as Lucas sequence, just like this. So the process is very simple to do, but by the simple construction rule, you can construct numbers in each row which happens to be a 1-1 correspondence, which can be put into 1-1 correspondence or a bijection rather with set of all natural numbers. But saying in simple terms, if you all these numbers are representing natural numbers in different order, so all these numbers together constitute the set of natural numbers. Okay, and there's no repetition here with any number. So that is the beautiful thing. So the simple construction helps us to make the bijection with set of natural numbers. In fact, one can prove that the element in this Wythoff sequence in the array form, like nth element in the kth column, is n minus 1 times kth Fibonacci number plus floor function of n times golden ratio phi times k plus first Fibonacci number. So I will explain this a bit. Suppose if we want to locate the second row third column element A23, according to this formula, you plug in n is 2 here and k is 3. So if you plug in those values here, you get f3 plus, see, golden ratio phi is 1.618 approximately. So 2 times 1.618 is 3.2 something. So you round off to the previous integer. So the floor function or greatest integer function is the integer, largest integer less than the given real number. Okay, so the floor function of 3.2, in simple terms, if the number is a positive, then the floor function discard all the decimal point, just take the integer point. So if it is 3.2 something, leave all the numbers after the decimal point, just take the integer point, which is 3. So 2 times p with floor function is 3. Third Fibonacci number is 2 here. You see, this is f0, f1, f2, f3. So third Fibonacci number is 2, and fourth Fibonacci number is 3, as you can see here. This is first, second, third, fourth. So they add up to 11. So this is 9 plus 2 is 11, and you can see here, verify from this table here, second row, third column element is 11. So similarly, if you can calculate fifth row 7th column element, that happens to be, according to this calculation, it turns out to be 220. Let us verify here. This is third row, fourth row, fifth row. So fifth row 7th column is here. So in fact it is 220. So by this formula, closed expression here indicated here for a n k, it is possible for us to express any number here in Wythoff's sequence. So it's not so well known, but it establishes a bijection between set of natural numbers and this particular sequence, terms of this particular sequence. This is in fact used in computer science in various allocation and array problems. Okay, so it's a very important sequence in computer science. Now going to the next possible sequence called Stern-Brokaw sequence, named after two mathematicians, Stern and Brokaw. Stern was discovered this around 1850s, around precisely I don't remember, but it should be around 1858. So around 1850s to 1860s he discovered this pattern. What he did was, he took a number of the form 1 by 1. Okay, and then he made this generation rule. If you start with a number in the form a by b, the left child, this number generates two new numbers. The left child is given by a plus b, whereas the right child is a plus b by b. So this is a generation rule in each case, with beginning with any number. So if I begin with 1 by 1, the left child is 1 by 2, because 1 by 1 plus 1. The right child is a plus b, which is 1 plus 1, 2 divided by b. So according to this prescribed rule, you can generate always two new numbers with a single number. So for example, from 1 by 1, I could 1 by 2 and 2 by 1. And similarly, I can continue this procedure to generate new numbers in subsequent rows. So from the number 1 by 2, I can generate 1 by 1 plus 2, which is 1 by 3, and 1 plus 2, which is 3 by 2. So this is the generation rule. The numerator is a, denominator is b. So the left child is a by a plus b, which is 1 by 1 plus 2, that is 1 by 3. And the right child is a plus b, that is 1 plus 2 is 3 divided by b. So 2. Similarly, you can generate using the same rule two childs from 2 by 1 to get 2 by 3 and 3 by 1 and all those things. So you can keep on doing this. So this looks like a tree structure in graph theory, isn't it? I mean, in fact, precisely speaking, it resembles what is called a binary tree, because binary tree is a tree in which there is a unique vertex of degree 2 that is called the root of the tree. So this is the root of the tree. But in strict terms, this is not a binary tree, because when we talk about tree structures in graph theory, tree structures will only have finitely many vertices. Okay, but I can continue this generation of numbers for infinitely many rows, because each time when you get a new number, you can make this rule to produce two new numbers, and therefore this procedure never stops. For the sake of fitting into a page, we have stopped onto this row. But actually speaking, you can use this rule again and again and again and iterate it to generate more and more required number of rows. So this resembles a binary tree, but not exactly a binary tree. But for the sake of understanding, let us stop here with probably with 5 rows I have written here. And even in 5th row, you see there are so many numbers. But you see the simple generation here of numbers in each row, again, as we saw in the previous case, could generate wonderful patterns. In fact, there are many patterns that we can discover here among these numbers. The first thing that you can discover is these numbers are all rational numbers, like they are positive fractions of the form p by q, where q is non-zero, and therefore you can put this set of numbers. So if you write this as a sequence, like 1 by 1, 1 by 2, 2 by 1, 1 by 3, 3 by 2, 2 by 3, 3 by 1, and all those things, writing from left to right in each row and putting them as a sequence, then that particular sequence will be bijection, will be in 1-1 correspondence with set of all positive rational numbers. In other words, this is another representation of set of all positive rational numbers. So in the previous case with Wythoff sequence, we saw 1-1 correspondence with set of all natural numbers. Here we get set of all positive rational numbers. Okay, so the simple rule enables us to generate numbers such that we can put 1-1 correspondence with positive rations. But the fun does not stop here. Actually speaking, you see that if you see the numerator and denominator of each of these fractions that we got here, or rational numbers, you see the numerator here 1, 2, and here the denominators are 2, 1. Here you see the numerators 1, 3, 3, 1, 3, 2, 3. Whereas if you see the denominator, it is 3, 2, 3, 1. So the denominators are exactly the mirror images of the numerators. You can see it in leisure. So here the numerators are 1, 3, 2, 3, whereas the denominator is 3, 2, 3, 1. Exactly the mirror image of the numerator. Because of this fact, they sum to the same number. Like if you add the terms in the numerator, that sum will be same as the sum of the terms in the denominator, because denominators are actually the mirror images of the numerator. Therefore, they have same sum. And what is their sum actually? So if you add 1 and 2, you get 3 in the second row. This is 1, this is 3. I'm just adding the numerators. In fact, that will be equal to the sum of the denominators because of the mirror image property. Now, if you add the numbers in the numerator in the third row, you get 1 plus 3, 4, 4 plus 2, 6, 6 plus 3, 9. So you see, you get powers of 3. If you add the numerators in each row, you get 1 in the first case, the second case you get 3, the third case you get 9, the next case you get 27, then the following case you get 81. So it is powers of 3. 3 power. Like Pascal's triangle has row sum 2 to the power n, which is well known to everyone. So this tree structure, Stern-Brokow sequence, will have terms like positive rational numbers in each row, such that the numerator as well as the denominators will add up to 3 to the power of n or 3 to the power of n minus 1, depending upon how you choose n. So if I choose n as the first row as n is 0, and this is 1, this is 2, then the row sum is 3 power n. Or if I choose the first row as 1 and then take this as 2, then it is 3 power n minus 1, depending upon how you choose it. Okay, so it is power of 3. That is what we can see. But the interesting fact doesn't stop here again. You can probably traverse from one particular number to other particular number, beginning with the first number, like 1 by 1. So what I'm going to do is I will make my path from one number to other number in this alternating sequence of left, right, left, right, left, right, left, right. So beginning with 1, listen, if I go 1 left and 1 right, 1 left will lead to me with 1 by 2. Then if I come to the right, I get 3 by 2. Did you notice this? See, if you see here, you get 3 by 2. This is a ratio of 2 consecutive Fibonacci numbers. So as you can see, the Fibonacci number here is 0, 1, 1, 2, 3, 5, 8, 13. So 3 by 2 is ratio of 2 consecutive Fibonacci numbers. So if I go to the left and then come to the right, suppose if I stop with left, then also I get a ratio of consecutive Fibonacci numbers. But in the case here, the lesser number is in the numerator, larger number is in the denominator. Whereas if I go to right, I get larger in the numerator and lesser in the denominator. Okay, so in either case, supposing if I go to further left, like left, right, left, if I go to the next term, left, right, this is left, this is right. Suppose if I go to left again, I get again ratio of 2 consecutive Fibonacci numbers, but numerator is lesser than the denominator. But if I go to another right, so I will consider sequence of left, then left, right, then left, right, L, R, L, R, L, L, R, L, R, L, R, L, R, L. So, I mean, 1 left and then 1 right, 1 left and then 1 right. You can keep on doing this. Each time when you go to left and come right, each time when you go to left, you always get ratio of consecutive Fibonacci numbers. And this is very, very interesting. In fact, it will be entertaining exercise for students. They can take this as a project work for if at all they are interested in doing. Like if I ask you, in which row and which place do you find the number, say 22 by 7 or say 13 by 6 or something, because I said that this structure contains all positive rational numbers. So it means any number that you take in the form P by Q, where P and Q are positive and Q non-zero, can be found in any one of these rows here somewhere, if you keep on doing this, okay, continuing this row pattern in this generation group. So if I ask you where does 22 by 7 will lie in this tree structure, or say 15 by 4 or something like that, it's a very interesting exercise for you to see where actually it does. And if you take the extreme left numbers, like 1, you get harmonic numbers, 1 by 1, 1 by 2, 1 by 3, which are reciprocals of natural numbers. Whereas if you take the extreme right numbers, you get 1 by 1, 2 by 1, 3 by 1, 4 by 1, which are natural numbers themselves. So the extreme right numbers are natural numbers, extreme left numbers are reciprocals of natural numbers, which are in mathematical terms called harmonic numbers, okay, because they form harmonic progression. Okay, so these are numbers in HP, and these are natural numbers forming in AP. So, and if you go left, right alternatively, you find the ratio of Fibonacci numbers. In fact, there are few other properties also, which might probably, for explaining those properties, I need to introduce new ideas to you, which I think it will consume more time because of other interesting sequences that I wish to deal with you. So, but those who find time after the session, you can go to the net and browse about finding all the properties. This is a very interesting part, and many young students can take this for the project work if they wish to do something. Okay, this is a very interesting thing. So the first case, I introduce a sequence which can be put into one-to-one correspondence with natural numbers. Second case, I have introduced another sequence of terms which explained in a, put in a tree structure, such that they have been put into one-one correspondence with positive rational numbers. Now we'll see some other sequences. Okay, so this is called look and say sequence, introduced by my very favorite mathematician, John Horton Conway, J.H. Conway. Now Conway was very special mathematician working in Princeton. Unfortunately, he passed away last year due to corona, COVID-19. In last April, he passed away. Breath is lost because of suffering from COVID, which is a very great loss to the mathematical community. In fact, I was so disturbed by his demise, because he was a mathematician with excellent ideas and wonderful mind. Very hard to see such a person. Okay. Anyway, so I introduced this idea in his tribute, okay, as a tribute to Conway. Now, so if you start with 1, the sequence, each term of the sequence goes like this. You start with 1, because there is only 1 here. First term 1 contains 1. So read the term here. 1 is 1. There's only 1 here. So the next term is 1. So you have to look and say the sequence and then write the next term. Now here the next term goes like this. There are 2 1s here. So for writing third term here, see, if I could have do this, write the terms in offline mode, this will be much better rather than writing the term beforehand. I don't know how many of you could follow this, but if you listen carefully, you can do. So the first term 1 contains 1. So the second term is 1. From the second term, I can generate the third term like this. There are 2 1s here, so the third term is 2 1. The fourth term is, there's 1 2 and 1 1. In 2 1 there is 1 2 and 1 1. So the fourth term is 1 2 1 1. And for the next term, there's 1 1 here and 1 2 and 2 1s. Okay. For the next term, 3 1s. So 3 1, 2 2s and 1 1. And similarly it goes on. So you see each term has more length than the previous term, or it might have same number of digits. It either stays at same number of digits or it expands with more number of digits. In fact, what Conway and his collaborators and his research students found a very interesting property here. If you assume that Ln is number of digits in the nth term of any look and say sequence. In fact, I need not have to start with 1. You can start with probably with a number like 36. 36 contains 1 3 and 1 6. And you see there is 1 1 here, 1 3 here, 1 1 here and 1 6 here. So that is how you can generate the next term. So there are 3 1s here, 1 3 here, 3 1s here and 1 6 here. So you can keep on doing this. So not necessarily starting with 1, you can start with any preferable number of your choice and then keep on doing the procedure. You get more and more terms with a very huge number of digits. Okay, but what Conway found was, if Ln is the length in each digit, so for example L1 for this particular sequence is 2 because there are 2 digits, L2 is 4, L3 is, you add up the digits, you get 8 digits here. So L3 is 8, L4 is also 8. Sometimes the number of digits might remain as it is, and subsequently also increase. So the number of digits in each term of the look and say sequence is non-decreasing. It stays at same level or it increases. Okay. So this is 4 plus 2, 6, 6 plus 4, 10. So this is 10 digits. So if you divide these, say the length of n plus 1th term by the length of nth term, Conway proved that it is always a constant as n is very large. So if n is very large, we keep on writing more and more and more and more terms as you like. Then in the limiting case, the length of the n plus first term is approximately 1.3 times the length of the nth term. So each term grows approximately 30% more than the previous terms. Okay, that is what Conway and his collaborators have found out. It's not a, of course, this discovery was not so long ago. It was made some few decades ago. In fact, Conway also went to the next step in showing that this number lambda, which is now called Conway's constant, is the positive root. This is the only positive root of the 71st degree polynomial. Okay, so you see here x power 71 and ends with 6 here, constant term minus 6. So he also showed that this number Conway's constant is the positive root of the 71st degree polynomial, which is quite amazing. I mean, Conway is master of all disciplines in mathematics. Okay, he was working at Princeton and a great mathematician. So those who are interested in reading about Conway's contribution can go and see. The important contribution that Conway made was inventing a mathematical game called life. Okay, so there's a very interesting computer simulation game which became very famous when it was discovered few decades ago. Okay. Now I will introduce what is called complementary sequences. Okay. Now I will generate two sequences. One is A of n, the other one is B of n, such that A of n contains floor function values of some number, irrational numbers, alpha and beta are some irrational numbers of observing some property. In fact, beta is and alpha beta will satisfy the condition 1 by alpha plus 1 by beta is equal to 1. So choose two irrational numbers alpha and beta such that they satisfy the relation 1 over alpha plus 1 over beta is 1. Okay, if you choose alpha and beta to be irrational numbers of that form and generate terms of the sequences A of n and B of n, which is greatest integer function of alpha, 2 alpha, 3 alpha, so integer multiples of alpha, and round it off to the previous largest integer. Okay, and similarly for B of n with beta. See, for A of n is for alpha, B of n is for beta. So if I choose the famous irrational number root 2, square root of 2, then A of n will look like the first term in A of n is greatest integer function of root 2. Root 2 is 1.4 something, 414. So the greatest integer function, as I told before, the positive for if the number is a positive real number, the greatest integer function or the floor function will just is obtained, the value of the floor function is obtained by just removing all the decimal digits after the decimal point and just take the integer point. So 1.414 and something so on. Yes, it has greatest integer. So discard all the terms after the point. So you get 1. So the first term is 1. 2 alpha. Alpha is 1.414 because alpha is root 2. So it is 2.828. So remove that 0.828 and so on. So you get only 2. Okay. 3 alpha. This is 4.2 something. So remove that 0.2 something and take 4. And 4 alpha is something. So you can keep on doing this to generate the terms of A of n. Now beta is a number which is actually, as I told you, is alpha by alpha minus 1 or something, because 1 by alpha plus 1 by beta is 1. So keeping in that sense, you can choose beta to be this number. So in fact, it is root 2 by root 2 minus 1, and simplifying that you get 2 plus root 2. So I start with the first term in generating beta of B of n like 2 plus root 2. Root 2 is 1.414 approximately. So this is 2 plus 1.414. This is 3.414. So the greatest integer will drop down to 3 because I have to neglect the terms after the decimal point. Okay. So it comes to 3. Then 2 times this. 2 times this is 4 plus 2 root 2. 2 root 2 is 2.8 something. And added that to 4, you get 6.8 something. So leave the decimal point, terms after the decimal point, you round it off to 6. So similarly, you get all these terms in B of n. Now, what is the speciality in getting these two sequences? You see, no term in A of n will be present in B of n. So they are complementary. And if you take union of A of n and B of n, you get the whole natural numbers. So A of n union B of n generates all natural numbers. In other words, no term of A of n will be present in B of n and no term of B of n will be present in. So they form disjoint subsets, two disjoint subsets of set of natural numbers. So if we want to make two disjoint subsets of set of natural numbers, this is the best possible way to do that. This was discovered by mathematician BT. So these are called BT sequences. Okay. Now, if you choose alpha to be golden ratio, the one of the best irrational numbers, and then do the same process, you get a of n to be this sequence, and beta, its complementary term. It's see, beta is actually alpha by alpha minus 1. So phi by phi minus 1, that turns out to be phi square, because phi square is phi plus 1 according to the rules of golden ratio. Okay. So B of n can be generated by this way, and you know golden ratio phi is 1.618 approximately. So phi square is maybe 2.56 approximately. So for B of n, the first term is greatest integer value of 2.5 something, that comes to 2. So you can in leisure time you can do this calculation, and again you find that no term in A of n is present in B of n. In a way, they are complementary sequences, and the union will form the whole set of natural numbers. So this is how you can split the whole natural numbers into two disjoint sets, making the partition for set of natural numbers. It's a wonderful way to do that. Okay. Now the next possible sequence that I can discuss with you is called Fibonacci or N-Nachi sequence. You are familiar with Fibonacci, but not many are familiar with Fibonacci and Quaternacci or Pentanacci or Heptanacci, Octanacci. Similarly, you can generate many such things. Okay. So for Fibonacci sequence, in Fibonacci you started with 1 0 and 0 and 1. You took only 1 0. For Fibonacci, you should start with 2 zeros and 1, and for generating the other terms, you have to add the previous 3 terms. So begin with 3 terms with 2 zeros. The first 3 terms are assumed by ourselves, like 0 0 1. So the fourth term is sum of those 3 terms. 0 plus 1 is 1, and the fifth term is second term plus third term plus fourth term. So sum of the 3 previous terms. In Fibonacci sequence, each term is sum of 2 previous terms, whereas in Fibonacci sequence, each term is sum of 3 previous terms, beginning with 0 0 1. Okay, so you have to start with 2 0 and a 1. Okay. For Quaternacci sequence, you have to start with 3 zeros and a 1. So assume 4 terms in which first 3 terms are 0 and the fourth term is 1, and each term thereafter the sum of those 4 terms, the previous 4 terms. So this term 1 is 0 plus 0 plus 0 plus 1, and this 2 is 0 plus 0 plus 1 plus 1. This 4 is 0 plus 1 plus 1 plus 2, that is 4, and this 8 is 1 plus 1 plus 2 plus 4. So each term is sum of 4 previous terms. Okay. That's how you can do it. And you can see the terms get larger and larger if you keep on adding, because as you increase the number of terms of addition, naturally the sum will increase. So we expect the terms to get larger. So the terms of Fibonacci sequence are much larger compared to the terms of Fibonacci sequence. And this is Tetranacci sequence, because we start with 3 zeros. Interestingly, you know that many knew the fact that the ratio of the successive terms of Fibonacci sequence is golden ratio, which is 1.618, which we were discussing in the previous example. The ratio of successive terms of Fibonacci sequence is the positive root of this polynomial, namely x cube minus x square minus x minus 1, that happens to be nearly 1.839 approximately. So in terms of Fibonacci sequence, it is 1.618 approximately. Here it is 1.8392 something. So I have given the expression called closed expression here. So the closed expression for golden ratio is 1 plus square root of 5 divided by 2. That is much simple. But here the things get complicated because this is a cubic equation. So the positive root of this polynomial contains cubic radical as well as a square root radical. Okay. Okay. And if you go for finding the ratio of the successive terms of Tetranacci sequence, it is approximately this number, 1.92756 and so on and so forth. That is the positive root of this. In fact, I have written a research paper proving that if you keep on increasing order of this Fibonacci, Tetranacci, Quaternacci, and all those things, eventually the ratio of the successive terms will approach to 2. So you see In golden ratio, it's 1.6 something, 1.618. For Fibonacci, it is 1.8392. For Tetranacci, it's 1.927. This is almost, you see, this is pretty close to 2, but not very close, of course. But you see that the ratio of the successive terms, when you keep on increasing the order of this sequences, beginning with Fibonacci, they approach to 2. So that's quite easy to show actually. You can use several methods in numerical methods to prove that, or by general view also you can make that. In fact, I have written a good paper on this also, proving that the ratio approaches to 2. And my other favorite sequence is bell number sequence. So the bell number Bn counts a number of different ways in partitioning a set. In fact, this is a very important sequence because the terms that we have written here actually represents a number of equivalence relations that can be defined on a set with n elements. So this is the number of equivalence relations, okay? Because you know equivalence relation will induce a partition of a set into disjoint subsets. In fact, bell numbers counts all such partitions into disjoint subsets. So that is how Bn is defined. Bn counts a number of different ways to partition a set that has exactly n elements. For the sake of students, I will just explain what you mean by bell number. If you take a set with just 2 elements, you can have just 2 set of partitions. Like you can partition is splitting a set into disjoint subsets. Either you can write the given set with 2 elements as AB itself with just one set, or you can write with A, singleton B. So there are 2 possible partitions that you can make for a set with 2 elements AB. Whereas for 3 elements ABC, you can have 5 possibilities here. So this is for 2 elements, and this is for a singleton set A. There's only one partition, namely itself. So this is 1. So if you take just one element set, there's only one partition possible. Of course, B0 is 1. For no element, we assume that the first there's only one partition, namely null set itself. And for one set with just one element, singleton A, the partition itself is itself. Therefore, there's only one partition with a single element. For a set with 2 elements, there are 2 possible partitions. Okay. For a set with 3 elements, there are 5 possible partitions. For a set with 4 elements and 5 elements, things are not so easy to compute. So there is a very nice expression here in terms of binomial coefficients. So Bn, the nth term, is sum over k 0 to n bk n minus 1 k. N minus 1 choose k. This is binomial coefficient. So if you are familiar with Pascal triangle, you can plug in these values from the Pascal triangle. As a model calculation, say the third bell number B3 is B0. If you put k 0 to 3 here, B0 k 0 to 2 rather. Okay. For B2, if you want to compute B, maybe I have done an error here in typing. There's a typo here. This should be B2, not B3. I'm sorry for that. So the first row here is computation for B2, that happens to be 5. Okay. So, no, that's not typo. B3 for Bn is n minus 1. That's correct. I was mistaken. Okay. So for B3, because Bn contains n minus 1, choose k. For B3, it is 2C0, 2C1, 2C2. That's correct actually. So for B4, so the formula here that I have represented here actually helps you to generate the subsequent bell number if you know the previous bell numbers. So for example, if you know B0, B1, you can plug in here to get B2. If you know B0, B1, B2, you can substitute that here as we did here, B0, B1, B2. If you substitute here and multiply by the binomial coefficients, you get B3. Similarly, if you know B0, B1, B2, B3, multiply each term with this formula with binomial coefficients to get B4. So if you know the previous terms of bell numbers, you can generate the next term. So what does this tells me? You can have 52 or 15 possible partitions for a set with 4 elements, and 52 possible partitions for a set with 5 elements. Therefore, there are 52 possible equivalence relations that can be defined for a set with 5 elements, and 15 possible equivalence relations that can be defined for a set with 4 elements, and so on and so forth. The bell numbers have this wonderful counting property. In fact, it has a very surprising connection with generating moments of Poisson distribution. In fact, you know, if lambda is a parameter of Poisson distribution, if I compute simple moments, that is E of x to the power r, For any distribution, E of x power 0 is always 1 because x power 0 is 1, so E of 1 is 1. E of x is lambda, as you know, mean of Poisson distribution is lambda. E of x square is lambda square plus lambda. E of x cube is this. So this can be done easily by probability ideas. You can use MGF or characteristic function to generate all these values. It's quite easy to do. We have so many methods to find the rth moment about origin or rth simple moment, E of x to the power r. Now if you put lambda as 1 here in this expressions, you get 1. Here it is 1, here it is 2. You get this numbers. You see, you get Bell numbers. If you put lambda as 1, you get 5. If you put lambda as 1, you get 15 here. So you can generate subsequent Bell numbers. So the Bell numbers not only have a connection with the counting number of partitions or number of equivalence relations, but it also have connections with getting the moments of Poisson distribution with mean 1. So take lambda as 1. Lambda is the mean of Poisson distribution. So I mean, it has a very surprising connection. In fact, it was discovered that it has this Bell numbers also has connection with Stirling numbers, another set of counting numbers which I have not discussed here. So those who find time can go and check it later. So B and the nth Bernoulli Bell number, the sum of the row numbers of Stirling's numbers of second kind. Okay. Now I will discuss what is called derangement sequence. What is a derangement? Derangement is a permutation in which none of the objects appear in the original order. So for the sake of understanding better, what I do is I take 1, 2, 3, 4, 4 numbers. You know that for n objects that you take, there are n factorial possible permutations, isn't it? If you keep on arranging two things, you get two factorial arrangements. Like if you take AB, you can put AB as itself, or you can put it as BA. So there are two factorial arrangements for two objects. For three objects, there are 3 factorial, which is 6 arrangements. For 4 objects, there are 24 possible arrangements. You can either put 1, 2, 3, 4, or you can put 1, 2, 4, 3, or 1, 3, 2, 4, whatever way you like. So you can keep on doing this way. Now, derangement refers to possible collection of terms in which no number is in its original position. Like I can't take this as a derangement because 2 is kept as it is, 3 is kept as it is, 4 is kept as it is, 1 is kept as it is. None of the numbers should be in its original position. So among these 24 possible cases with 4 elements that we have taken, how many elements here will be such that none of the number will be placed in its original place? Like the red boxed elements or arrangements will be a derangement because 1 is changed to 3, 2 is in 4, 3 is in 1, 4 is 2. But this won't be counted because 4 is in the place of 4, though those 3 numbers vary. 1 is going to 2, 2 is going to 3, 3 is, so these 3 numbers are changed their position, but 4 is kept as 4 itself. So this is fixed. None of the symbols should be fixed here. So such an arrangement is derangement. So completely changing. None of the element that you take should be in its original position. Okay, that is what is called derangement. So among 24 possible permutations, you find that there are only 9 arrangements that comes to the case where none of the elements is in its original place. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the only 9 possibilities in which every number changes its position. None of the element is in original place. In fact, if you can form a sequence with just one element, you can't change one element. I mean, you can't make any permutation by changing one element. So there's no possible derangement with one element. So the first element is 0. But with 2 elements, you can make one derangement, because if you have 1, 2, you can change it to 1, 2, 1. So 1, 2 can be changed to 2, 1. So there is only one derangement for 2 elements. For 3 elements, there are 2 derangements. For 4 elements, as we saw here, there are 9 derangements. So how to compute this now? So there is you can, of course, for the want of time, I'm just skipping this. There's a wonderful formula that you can have a proof of finding this using principle of exclusion and inclusion, or inclusion and exclusion, whatever you call it, for proving this. So I'm just skipping this proof here for the want of time. Okay, so this is this is called subfactorial, SUB, just like subset. This is called subfactorial. So the symbol for derangement is either subfactorial or d of n, for d for derangement. So subfactorial of 4 is d of 4 according to this particular formula is 4 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial up to 4 factorial. You can do this, so you get 9 as we got here. So for 24 possibilities, only 9 comes as derangement. For 5, you can use this formula, it comes to 44. So that 44 is present here, you see. So you can generate a nice formula. In fact, there is a recursive formula for finding derangement with n elements. And interestingly, if you take the limit of derangement by, subfactorial by factorial, derangement of n divided by n factorial. So this formula comes here. See this, if you divide this by n factorial, you get this summation value, and this is simply 1 by e, which is e to the power of minus 1. This conveys an important meaning here. This, it doesn't matter however you dislocate the element, even if you do the worst thing, you can maximum possible way you can do that only approximately to 37%. So even in the worst possible case, it is not possible to go beyond 37% or 36.7% to dislocate anything. So this is very, very efficiently used in several optimization problems. Okay, so this sequence gives that particular information, and then I will probably discuss what is called a juggler sequence. So the k plus first term ak plus 1 is graded integer of square root of ak if ak is even, and ak to the power 3 by 2. So that is integer value of ak to the power 3 by 2 if ak is on. Okay, so this was introduced by a very famous computer scientist and a mathematician, Clifford Pickover, who was one of my very favorite mathematicians, American mathematician. He has written wonderful books, nearly more than 40 books he has written in mathematics, in popularizing mathematics. He is one of my very favorite authors, Clifford Pickover. Okay, so in one of his books, he has mentioned about this juggler sequence. It's called juggler because if upon juggling the balls or the objects the juggler makes will go up and come down in zigzag fashion. So the terms here goes up and comes down in zigzag fashion. So Clifford Pickover choose to keep that particular term for this sequence, and therefore it is called juggler sequence. Supposing if I start with first term 3, see if I take an odd number here, then the next term is that number to the power 3 by 2 greatest integer. So 3 power 3 by 2 is 5.196 greatest integer. So discard all these values after the decimal point, you get 5. Because the number is odd, again use this point here. 5 to the power 3 by 2 is 11.18. So discard all the decimal digits after the decimal point, you get 11. If you keep on, because 11 is odd, I have to, whenever the number is odd, to get next term, use this formula. Whenever the number is even, use this formula. Okay, so you get 36 here, the third term. Because this is even, I have to take the square root of 36. 36 to the power half, which is 6, and greatest integer of 6 is 6 itself. Because this is even, so then get the next term, you get square root of 6, which is 2.449. So greatest integer turns out to be 2. So the next term you get 2 power half, because it's an even number. For the even number, I have to choose this function. Okay, so 2 power half, this is square root of 2, that is 1.4 something, which is 1. So what Pickover wrote a program, computer program to see this fact. In fact, if we start with 2 as initial term, 3 is what I have. We have considered 3, 5, 11, 36. So the terms corresponding with the initial term 3, or there are 7 terms here before it ends with 1. So what Pickover saw with this computer program is that it doesn't matter which number you start with, it always ends with 1. Surprisingly, this fact was not yet true, though this was discovered by, or rather observed by Pickover some 2.5 decades before. This was not even proved now. So this remains one of unsolved problem in number theory. So, but it is quite not so easy to do, as we saw in previous examples, also in 3n plus 1 problem that I was discussing in my previous lectures. This is notoriously difficult. But the wonderful thing is the terms go somewhat very, very large. Even for some starting terms, the terms go up to million, and then it drops down to 1. That is why the term juggler sequence is mentioned here. Okay, it goes as far as, and people verified up to 1 billion terms. the computer has checked up to 1 billion terms. For all such initial terms, the sequence always ends with 1. But that is not a proof, I mean, there is only a verification. And my last sequence that I probably have to discuss with arithmetic number sequence. So these are numbers for which if you add the divisors of the number. So for example, if I take 1, the 1 only divides 1. Now for 3, so that's a trivial case, so leave it. For 3, what are the numbers that divides into 3? 1 and 3. You take their average. So average of 1 and 3, average of the divisors. 1 and 3 is 4. So 4 divided by 2 is 2. If the average of the divisors of a number is a positive integer, if it's an integer, then such number comes as a member of this particular sequence, arithmetic sequence. It won't work for 2. 2 doesn't come here because the divisors of 2 are 1 and 2, and their average is 1 plus 2 is 3. 3 divided by 2 is 1. So 1.5 is not an integer. So 2 doesn't come here. Similarly, for 4, if you take 4, the numbers that divides into 4 are 1, 2, and 4. If you take their average, you get 1 plus 2 plus 4 by 3. There is 7 by 3. That is again not an integer. So 4 doesn't come here. Whereas if you take 6, 6 comes here because the divisors of 6 are 1, 2, 3, and 6. If you add them, you get 12. 12 divided by 4 because there are 4 divisors. So 12 divided by 4 is 3, and there is an integer. So you see at least 2 observations here from this, that all prime numbers except 2 will be a member of this sequence. So except 2, all prime numbers will be an element in the sequence, because if p is an odd prime, then the only possible divisors of odd prime is 1 and p being odd, 1 plus p is even, so that is divisible by 2. So the resulting average is always an integer. Therefore any odd prime p will always be a member of this particular sequence, and 2 doesn't belong to this. So except 2, all prime numbers have been an element of this sequence. It's a very interesting sequence. And interestingly, the density of the sequence, you can refer what it means by density later. The arithmetical density of the sequence is almost 1. It was proved by Paul Ladish and other great mathematicians. And the other interesting aspect that you can find here is a number belong to this sequence if the number of divisors of that number divides the sum of the divisors. So if the number of divisors of any number divides the sum of the corresponding divisors of the number, then such number will be a term of this. Okay, so this is how it comes to. So for example, if you take 15, 15 has 4 divisors, namely 1, 3, 5, and 15. They sum up to 1 plus 3 plus 5 plus 15, that is 24. 24 divided by 4 is 6, that is an integer. Therefore the number of divisors, namely 4, divides the sum of divisors, namely 24. So if that being the case, then such a number is arithmetic number sequence. There are a lot of mathematics that is lived with all these ideas. So what I can probably conclude before, say to you, being young students and research scholars, is that there are plenty of opportunities available, even with basic ideas in number theory. So it's up to you to explore all such things, and there are wonderfully many sequences. In fact, when I was preparing this, I had actually put 5 or 6 more sequences of my choice, but seeing that there's only 1 hour available, I discarded those sequences. Probably if chance occurs, I will continue in the upcoming time. But I hope that this have motivated you to think. See, all the sequences that I have mentioned, the terms of such sequences can be generated very easily. In fact, they're a very charming way you can do that. But they have surprisingly many connections to counting problems and many other applications in some other fields also in science and technology. In fact, there are so many sequences which have beautiful applications in science and technology. Like, for example, Catalan sequences have abundant applications in so many counting problems and other fields of applications. Stilling sequence and other sequences. There are wonderfully many sequences. But what I have chosen here is somewhat beautiful sequences, but not quite popularly known. So that is my idea. So I hope this has kept you engaged for 1 hour time or whatever it is. If there are any questions, I'd be happy to answer. I conclude my talk with this. So I thank our head of the department, Professor Venkatramanan, and the organizers and the whole mathematics department as well as the management for giving me this wonderful opportunity of sharing what little I know with you.
Thank you, sir. Sir, I think no questions in chat box, sir. Sir, no questions, sir, in chat box.
Any questions?
Sir, no questions, sir, in chat box. Okay, sir.
I think if there are no questions, we can conclude.
Okay, okay, sir. Thank you, sir. I'm very grateful and honored to propose a formal vote of thanks. On behalf of Postgraduate and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnav College, I thank our resource person, Dr. R. Sivaraman, Associate Professor, Postgraduate and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnav College, Chennai. We thank you for spending your valuable time in this session to sharing your knowledge in view of motivating and encouraging students, sir. Thank you, sir. Dear participants, feedback link posted in the chat box. Kindly fill the feedback form. After filling the feedback form, you will receive the participation certificate. Our next webinar titled Some Applications of Graph Theory, resource person Dr. N. Jayan Karthik, Associate Professor, PG and Research Department of Mathematics, DWARAKA Govardhan Das Vaishnav College, Chennai, which will be held tomorrow at 2 p.m. Thank you.